Namaskar. So in this week we discussed about linearity of the circuit, and then we discussed about the source transformation, and in last class we discussed about duality. So with the reference of these three important properties of the circuit, let us start the network theorem, which is called as Thevenin's theorem. And this Thevenin theorem is very important for the circuit point of view. What happens in generally that the particular element in a circuit which is variable, generally that particular element is considered as a load, and while the other elements are fixed. You can take typically the example of household outlet terminal that may be connected to different appliances. So what happens when you plug in your appliance in the house, you will analyze the voltage and current parameters of that appliance while neglecting the circuit which is outside the particular plug point. So what happens that you will analyze the circuit parameters like voltage and current while doing the analysis for various appliances. So various appliances will have their own current level, while voltage level will almost remain same in all the appliances. So in that scenario, if you are doing the study for appliances, how you will analyze the circuit? If you see the conventional way of circuit analysis, what you have to do? You have to take the complete power system network that is very large in size, and you will end up having hundreds of mesh networks or hundreds of nodes in the network. And if you start doing the mesh analysis or nodal analysis, it will take a lot of time, and it will be almost impossible to do it in a reasonable time frame. So to address that problem, the alternate way is that you can represent the equivalent of the power system network which is external to that particular plug point, and then analyze only that particular load or that particular variable element in which you are basically interested. So to solve that problem, we use the theorem called Thevenin's theorem, because it provides a technique by which the fixed part of the circuit is replaced by its equivalent circuit. Now according to Thevenin's theorem, the linear circuit in the left of the figure which is shown below can be replaced by that shown in the right. So if you can imagine that these are the two terminals of your plug point in the house, external to that you will see as a linear circuit. So you have to keep in mind that Thevenin theorem work well when the circuit is linear. So you will assume that the circuit which is outside your plug point is the linear circuit, and you will replace that particular segment with one equivalent circuit where you will have one voltage source and one resistance. So in that way, the load which you are analyzing for various circuit elements like the variables like voltage and current, you will keep that load connected with the equivalent of the circuit which is external to that particular load terminal. So that circuit to the left of this, the node AB, is called as Thevenin equivalent circuit. This concept was developed by M. Leon Thevenin in 1883, who was a French telegraph engineer. So what does Thevenin theorem says? A linear two terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH in series with resistor RTH, where VTH is the open circuit voltage at the terminals and RTH is the equivalent resistance at the terminals when the independent sources are turned off. So, when we calculate the value of RTH, we will create the equivalent circuit by switching off the independent sources. Switching off the independent source means if you have an independent voltage source, you will short circuit, and if you have an independent current source, you will open circuit. So, the problem with the Thevenin theorem is that you have to identify the ways how you will calculate the value of VTH and RTH. Now, if you assume that there are two circuits which are shown below are equivalent, that means there is an unknown linear network where we do not know what is inside, and outside that linear two terminal circuit we have connected a load across terminals A B. So, voltage across terminal A B is V and current flowing into the load from the external circuit is current I. So, if we replace the external circuit with Thevenin equivalent, that is voltage Thevenin voltage VTH in series with one resistance RTH, and if you have VI characteristic at this terminal same while taking the load out, then this particular circuit will be considered as a equivalent of that external circuit. So, you have to keep in mind that these circuits are said to be equivalent only when you have voltage current relationship same for both of the circuit at their terminal. Now, when the terminal A is circuited, by removing the no current will flow through the load. Now, this open circuit voltage across the terminal AB in the circuit on the left must be equal to voltage source VTH in the circuit on the right. So, that means that if you remove load from here, there would be some voltage across terminal AB, and if you remove load from here, there will be same voltage which would be coming across AB, that is V. So, using this particular equivalency, you can identify the voltage of VTH. How? Because VTH is open circuit voltage across the terminals. When you remove the load, you will see some voltage, let us say it is VOC. Similarly, for the Thevenin equivalent, that is here, if you remove the load, you will again get the value VOC, and these two VOCs are same because this VOC would be nothing but VTH, because when it is open circuited, there would be no current flowing in this particular segment, right. So, if you remove these the load, no current will be flowing. So, in that case, this particular voltage would be nothing but VTH. So, what we can say that the linear two terminal circuit open circuit voltage across terminal A B would be equal to VTH. Now, again with the load disconnected across the terminal A B, then you have open circuited the terminal A B, all independent sources you need to turn off. Turning off the independent sources means if you have the voltage source inside the terminal, you will replace it with the short circuit, and if you have current source, you will replace it with the open circuit. So, in that case, what will happen, that this linear two terminal circuit would be nothing but a dead circuit because there is no source available. Now, the equivalent resistance which you will measure between these two terminal A and B would be equal in both of the cases. Both of the cases means the case 1 where you have linear two terminal circuit, you will take all the sources off, you will measure the RTH here. Similarly, if you measure RTH here, it will be this value, because in that case this would be short circuited. So, in that case whatever the resistance you will see in both of the cases, the input resistance which you will see across the linear circuit with all independent sources set equal to 0 would be equal to RTH. So, with these two conditions you can find the value of the important parameters which are required for Thevenin theorem, which are VTH and RTH. Now, to find out the value of RTH, there are two different cases. What are the two different cases? First case is that if the network has no dependent sources, we can simply turn off all the independent sources, like we can make the voltage as short circuit and current source as open circuit, and then RTH is the input resistance of the network looking between terminal A and B. So, that means that whatever the input resistance you will see from terminal A, B, while keeping all independent sources equal to 0, that will give you simply the Thevenin resistance. Now, in case 2, when the network has dependent sources also, we cannot switch off the dependent sources because they are anyway controlled by some circuit variable. So, what will happen in that case? You can simply turn off only the independent sources. So, you will only switch off independent sources while keeping dependent sources on, and then you will analyze the circuit. How? You have to simply apply one voltage V naught at the terminal A B and determine the current I naught. So, what will happen in that case? Here the circuit with all independent sources equal to 0 are present and the dependent sources are also available. So, in that case you have to apply one voltage V naught across the terminal of AB and measure the value of current I naught. Then V naught divided by I naught would be giving you the value of Thevenin equivalent resistance, that is RTH. Alternatively, the RTH can also be measured by inserting a current source. So, instead of voltage source, across these two terminals you will apply one current source. Now, what you have to do? When you apply the current source, instead of the current which you have measured here, you have to measure the voltage across terminals A, B. What will happen in that case? Again, the RTH would be given as the voltage across terminals A, B divided by the current supplied by current source. So, in that case the RTH would be nothing but V naught upon I naught. Now, in both of the cases you can use any one of the method. In both of the cases you will get the same value of RTH. So, you will get eventually the same result. Now, it often occurs that the RTH which you calculate will become negative. So, it implies that the circuit is delivering power. So, you need not to worry whether your solution is correct or not if your RTH is negative. So, sometimes RTH would be negative, and it is also possible when the circuit is having dependent sources. Now, this theorem is very important in the circuit analysis. Why? Because it helps in simplifying the circuit. So, whatever the larger network outside the area of your study is present, you will simply equivalent that network which is outside the area of your study by Thevenin equivalent. So, you will replace with the VTH and RTH, and you will use that particular equivalent circuit to analyze the circuit which is of your interest. So, that is why this the Thevenin equivalent replacement technique is very powerful tool in our circuit design. Now, as we have discussed that linear circuit with variable load can be replaced by Thevenin equivalent excluding the load. Now, this equivalent network will behave as same way as the external circuit is behaving, because you are creating the Thevenin equivalent of the external circuit by keeping VI characteristic equivalent. So, how you will calculate the different load voltage and load current values? Let us take one sample circuit and we will try to find out the value of current flowing through the load resistance RL. Now, what you will do, the circuit external to your load RL would be replaced by its Thevenin equivalent, that is VTH and RTH. So, what will happen in that case, the circuit RL, this would be your load, and there will be one resistance RTH would be the Thevenin equivalent resistance, and it will both would be connected through voltage source, which is nothing but Thevenin voltage. So, this would be the equivalent circuit of your the original circuit, where the linear circuit is not known to us. We are just simply replacing it with the Thevenin equivalent. Now, how we will calculate the value of current IL? Simply, the value of current IL would be the voltage VTH divided by RTH plus RL. So, that is simply the Kirchhoff voltage law you can apply and get the value of current IL. Now, the voltage across load, that is VL in this case, would be IL into RL, and you will simply get the value of VL as VTH into RL divided by RTH plus RL. So, when you get the values of RTH and VTH, you can easily find out the variables across the load, that is voltage and current. Now, if you have multiple cases or multiple loads through which you want to find out the current and across those loads voltages, you need not to change anything in this circuit, that is RTH and VTH. You have to just keep on changing the loads across terminal A and B. So, based on the resistance of the load, your load current will keep on changing. So, in this way it will be very handy to process the multiple cases when these are connected to two terminals. Now, let us understand this particular aspect with the help of one example. Now, you see there is a circuit given in this figure. We need to find out Thevenin equivalent to the left of terminal AB. So, these are the terminals AB, and we have to find out the current through the load when RL is equal to either 6 ohm or 36 ohm. So, this is the variable load, it will keep on changing. So, you need to find out the value of current through the load under various loading conditions. So, for this particular case we are considering two different loading conditions where RL is 6 ohm and 36 ohm. Now, how we will do? We find the Thevenin resistance by turning off the 32 volt source. Now, when you replace the voltage source, it will become short circuited, and we have another source which is current source, that is 2 ampere current source. So, we will simply make it open circuit. So, what will be the updated circuit in that case? We are left with only the 4 ohm resistance in parallel with 12 ohm resistance and then finally the parallel combination in series with 1 ohm resistance. So, what happened when you make the equivalent circuit, the resistance which you will see through these particular terminals, that is A and B, you will get the value of RTH as 4 ohm, because the parallel combination of these two resistances would give you 3 ohm plus 1 ohm in series. So, finally, the RTH value is 4 ohm. Now, next step is finding out the value of Thevenin voltage. To find the value of Thevenin voltage, we have to consider the circuit, and whatever we discussed in previous classes, we have to just recollect our study, especially the mesh analysis which we discussed, because here it is, you can see that you can create two meshes, you can apply mesh current I1 and I2 across these two meshes, and you need to find out the voltage VTH across terminal A, B. Now, important thing which you need to see from this particular circuit is that current I would be 0. Now, when current I is 0, the VTH would be applied straight away across this, that means the same would be applied across this, because all are in parallel. So, VTH would be nothing but the voltage which is coming at this particular node. So, VTH would be the value of this node. Now, let us apply the mesh analysis for these two loops. For loop 1, when you apply the mesh analysis, what you will get? You will get, when you start from here, you will get minus 32 volt, because it is the current, mesh current is flowing from minus to plus, this will be minus 32 plus 4 I1, then 12 I1 minus I2, because I1 would be flowing in this direction, I2 would be flowing in this direction. So, net current would be I1 minus I2. So, this will become 12 into I1 minus I2, and that would be equal to 0. So, this is the first equation which you get from mesh 1. Now, if you see the mesh 2, you can straight away see that current I2 is nothing but opposite of the current source current value, that is 2 ampere. So, you can simply write I2 is nothing but minus of 2 ampere. So, now you have got two equations, I2 you have straight away found. Next is, you have to just place the value of I2 in this equation, and you will get current I1 as 0.5 ampere. Now, as you have got value of current I1 and I2, what you have to do? VTH would be nothing but 12 into I1 minus I2. So, you can simply write the value of VTH as I1 minus I2, simply put the value of I1 and I2, you will get VTH as 30 volt. Now, instead of mesh analysis, you can also apply nodal analysis as well. So, if you apply the nodal analysis at this node, because this is the node where you are seeing the voltage VTH. So, if you apply nodal analysis, that means that you have to use Kirchhoff current law here. So, what will happen? You will simply see what are the various currents flowing into the node and equate it equal to 0, because total sum of current at that particular node would be 0. So, what would be the current coming inside from left? That would be 32 minus VTH divided by 4 ohm. So, you have got first term of the equation. Then next is 2 ampere current which is flowing in this direction. So, you can simply put the value of 2 ampere. Third is the current which is flowing in this direction. So, the current flowing in this direction would be sum of these two currents. So, finally, this would be equal to VTH by 12, because the voltage at this is VTH and the resistance connected between reference node and the node in the question is 12 ohm. So, you will simply get this equation when you apply the nodal analysis. Now, if you rearrange the terms and simplify it, you will again get the value of Thevenin voltage, that is 30 volt. So, in that way, either you apply mesh analysis or the nodal analysis, in both way you will get the Thevenin voltage same. Now, your equivalent circuit of the particular figure which we discussed is 30 volt, that is VTH, and 4 ohm, that is RTH, and across the terminal A B you will apply variable resistance, where you have to find out the value of current, load current for 6 ohm and 36 ohm. So, what you will do, you will just put the value of RL. When RL is equal to 6 ohm, you will simply get IL is nothing but you will simply apply Kirchhoff voltage law, and you will get the value of current IL as 3 ampere. Similarly, if RL is 16 ohm, you will get current IL as 1.5 ampere. When you will replace RL with 36 ohm, you will get IL is nothing but 30 divided by the value 40. So, you will get 0.75 ampere. So, in this way, the benefit which you will get is that you will keep the left of this particular segment, left of the terminal AB same, and you will keep on varying the load resistance, and you can find out the value of load current when various load resistances are given. So, in this way you can calculate the value of the load current for various loading conditions. So, we stop here with the initial discussion on the Thevenin theorem, when we considered only the independent voltage or current sources. In next session, we will discuss the case where we have dependent voltage or dependent current source is also available in the circuit. In that case, how we will analyze the circuit. Thank you.